This lecture segment introduces macros, which are parameterized pound defines that are used like function calls. These are important tools, but they're tricky to design right, and we'll discuss how to do this. The C preprocessor accepts pound defines with parameters. Such parameterized pound defines are usually termed macros. Min1 on line 3 here is a good example. You may list any number of parameters after the pound define name, and then use them in the substitution string that follows. The parameters take no types. They're just placeholders that are filled in with string patterns when you use the macro, like down here. When you use the macro in code, you add actual parameters in parentheses after it, like the I and j on line 16. The preprocessor replaces the placeholder parameters with the actual parameters in the replacement string. So, for instance, if I were to have written min1 alpha I plus j, as in the transcript, then that would substitute to alpha less than I plus j, question mark alpha colon I plus j. Or, as on line 16 we'll see, min1 ij substitutes to I less than j, then I else j. These expressions compute the minimum of their respective parameters. The one in the transcript computes the minimum of alpha and I plus j, and the one here in the code, the minimum of I and j. So the min1 macro behaves like a function call, computing the minimum of its two arguments. But to be clear, there is no function call. The preprocessor just replaces each instance of min1 plus parameters with an expression that computes the minimum of those parameters. The preprocessor has no understanding of C. It's a mindless string substituter. So, for example, if you write min1 stupid preprocessor, comma, it can't tell prose from code, then the preprocessor, like some digital parrot, replaces this with stupid preprocessor less than it can't tell prose from code, question mark, stupid preprocessor colon it can't tell prose from code, like this in other words. And of course you'd get compile errors from the substitution. This mindless substitution behavior results in several design problems with macros, which are covered and mostly solved in the following discussion. So, to that end, let's now go through several common problems with macros and show how to fix them. I'll ask you repeatedly in upcoming in-lecture questions to take a misbehaving macro call and make the macro substitution by hand to figure out why it fails. You could do this mechanically via compiler option -e, but for this lecture, please do it by hand to reinforce the ideas. Now, line 16 makes simple use of min1 to print the minimum of I and j. And as you can see in the line 28 output, this works as advertised, printing 42. But line 17 attempts to use the result of an assignment operator as the first parameter, expecting that k will be set to 44, and then the min of k and j would be computed. As the line 29 output shows, the min is 43 as expected, but k is set to 43, not 44. And so we come to question number 1. Why is k set to 43? Make the substitution by hand and look closely at the result with operator precedence in mind. And if you still don't see the answer, then parenthesize the substitution fully according to precedence rules. That may help. Coming back from a pause, the transcript has the answer, but I've also got a little covered -e output here so that we can see exactly what the compiler sees. So the substitution is k equals 44, then j, or less than j, I'm sorry, question mark, k equals 44, colon j. But operator precedence, as you can see in the parenthesized version in the transcript, would perform this as k equals, and then the collective expression 44 less than j, yada yada, because conditional, question mark, colon, has higher precedence than assignment. So the inner assignment does put a 44 into k, but the conditional expression beginning at 44 computes the value 43, because the minimum is j of 43, and the result of that is then assigned into k, and that is why k is 43. Now, let's call this internal operand stealing. That's a private term, by the way. There's no general term for it. If you call a macro with expression parameters, then precedence rules within the substitution may cause some of the operands, like that 44, to be stolen by other parts of the macro. The fix is straightforward, but a little bit ugly. What we do is fully parenthesize every use of a parameter in the substitution string, as in min2 here on line 4. Now, that macro, if we'd used it instead, would have put parentheses around the k equals 44 instances, and so they would have been done as a assignment unit and then used as part of the larger conditional instead. Even min2, though, has some problems. Line 19 uses min2 to compute the minimum of I and of j, and then add 1 to it. But as you can see on line 30, this fails when they're passed in one order. Min I comma j plus 1 does not work, but it succeeds when they're passed in the other order. So question 2, second one in 43 works. Question 2, hand substitute this min 2 I comma j plus 1 and consider precedence to figure out why it returns 42 instead of the expected 43. Again, coming back from a pause here, let's go down to our little substitution block, and we'll find that what it yields is this. I less than j, nice and parenthesized, I, otherwise j plus 1. Oops, the addition is going to be done first. Addition has higher precedence than conditional. And so the j plus 1 is the final operand of the conditional. But the test, I less than j, is actually true, so the result is I, 42. Now, let's call this external operand stealing. If you call a macro as part of a larger expression, then precedence rules may cause part of the larger expression to be stolen by the macro substitution. And again, the fix is straightforward and ugly. All we have to do, as in min 3 on line 5 here, is fully parenthesize the entire substitution string as well. And that would have fixed the problem on line 19. Now, obsessive parenthesizing of macros can prevent operand stealing of both sorts. But, as line 20 illustrates, we're still not out of the woods. Here, we want to post-increment I and find the minimum of the old value of I, it is a post-increment, right, versus j. We'd expect a minimum of 42 and a new value of 43 for I as a side effect. But instead, the result on line 32 shows 43 for the minimum and a value of 44 for I. So they're both one larger than we would have expected. And question 3, of course, why all these results even after all that parenthesizing? Do the substitution. And again, looking down at the compiler output here, the -e output, the substitution yields I++ less than j, question mark, I++, colon j. The thing is parenthesized up to its ears, but this doesn't change the fact that I++ is done twice, because it was substituted twice. Even though the test is true, post-increment yields 42, I has 43 by the time the true branch is evaluated, and evaluation of the true branch in turn raises I to 44. So the thing returns 43 and leaves I at 44. Now, this one, sadly, has no easy solution. We'll see some other macros for which it is solvable later, but this one, it isn't. If an argument is substituted more than once into a macro string, then that argument must not have side effects like incrementation, or they'll be done twice. There is actually a term for parameter passing in which the actual parameter literally substitutes for the formal parameter, as in macros. You should already know, by the way, call by value and call by reference parameter rules. Reference earlier lectures on that. This macro-like parameter passing is call by name. It's characteristic of any substitution mechanism like C's macros. And as you can see from the just noted bug, it's rather a nuisance. Brief aside here, remarkably there was an early C predecessor language called ALGOL in the early 1960s. It had call by name behavior for function parameters, even though they were compiled, not string substituted. Doing this required some serious cleverness, and wasted cleverness at that, because call by name is really bad parameter behavior. It's just one you're stuck with if the underlying mechanism is a substitution system, and languages after ALGOL ditched it altogether when they possibly could. So far our macros have expanded to expressions. Let's try another type of macro now instead. The ones that expand to expressions acted like value returning functions. But this other possibility is a macro that expands to a multi-statement block of code. Macro swap on lines 7 through 11 here is a good example. It expands to a code block, complete with a block scoped variable under swap temp, and 3 assignments that swap the 2 parameters x and y, using it as on line 23 down here, results in the macro use being replaced by that entire 3-statement block, which exchanges I and j, as the line 32 output down here demonstrates. Now, statement block macros can be more powerful than single expression macros, but they act like a void function, performing some action but returning no value. Single expressions can return a value, but code blocks, I should say, cannot. Now, technically, one cannot break a macro substitution string over many lines. It must go on just one. But the preprocessor lets you escape a return at the end of a line by preceding it with a backslash, as we do on lines 7 through 10 here. This is like adding a just kidding to the return, and the preprocessor will ignore the return, omitting it from the substitution string. So you get to look at something rationally indented, while the preprocessor still sees it as a single line. And you can see that in the final line of the -e output down below in the diagram, where the result of that swap substitution is here on just one line. Now, the bad news is that it's really easy to put a space after the backslash and then a return. If you did that, say put a space right there, then you're escaping the space, not the return. And you'll get odd preprocessor errors. So watch out for this one. It's easy to do and it's hard to see. Okay, so now I can swap any 2 variables using swap without the overhead of an actual function call and the messiness of passing addresses, which would have been needed for a conventional swap function. But if I have an array A, let's see, and an integer I, whose value is within the index range of the array, and I swap them by calling swap I AI, I'm going to get a seg fault, almost certainly from that. But if I exchange them the other way, that would work. Let me put them up here in the diagram. So substitute out, there it is in the diagram. The first one would cause a fault in at least a lot of reasonable cases, and the second one will work okay. So I'll explain why that is the case. Again, of course, by doing the substitution. And coming back from a pause, let's look in the transcript here. It's a little lengthy to put in the diagram. The substitution for the first case will take I and put it in swap temp, and then copy A bracket I, Lord knows what that might be, into I. And then the third assignment is using the new value of I, which was some original value from AI and is probably out of range, and thus causes a seg fault. At the very least, it does the wrong thing. On the other hand, if I had them in the order with A bracket I first, then A bracket I goes into swap temp, and then I goes into A bracket I, and then I get swap temp, and in that case, it actually works. So, call by name strikes again. Question number 5. What's with this name under swap temp? Why did I feel compelled to give such a strange name to the macro temporary variable here? It's valid, but it's pretty odd looking. Wouldn't a simple temp have done just as well for this purpose? What specifically could go wrong if the macro used temp here instead of under swap temp? And note, by the way, that any variable declared inside a code block is local to that block. So swap's block local temp would be distinct from any temp variable in the calling code. Coming back from a pause. Okay, well, it won't go and modify a temp variable in the calling code per se, unless, of course, the calling code actually passes a variable named temp as one of the arguments. Then the substitution would be totally messed up because, say, x and the local would be the same name. So, call by name strikes yet again. And we add obscure naming of block local variables to the list of protective design measures in macros.